Welcome to the next lecture on factorial experiment. So, you may recall that in the earlier two lectures I had given you a background that why do we need these factorial experiment, and particularly in the last lecture I have taken a very simple example of 2 square factorial experiment where I had taken 2 factors, irrigation and nitrogen, and both were at 2 levels. And then we had 4 observations using the 4 possible treatment combinations of irrigation and nitrogen, and using those 4 values we have tried to understand that how these 4 values can be combined in different ways to find out different types of effects. For example, we found the main effect of irrigation, we found the main effect of nitrogen, and we found the interaction effect between irrigation and nitrogen, and we also found the general mean effect. So, now I am going to extend the same expression in a more general setup. We had considered those general setups in the earlier lecture also, where I had denoted the factors I and n by here capital A and capital B. Their levels were denoted as A0, A1 and B0, B1. So, now I am going to make it say more formalized. I am going to explain it in a more formalized way now. So, now let me give you a quick review. In the last lecture we had considered a 2 square factorial experiment where there were 2 factors A and B, and these factors were denoted by capital A and capital B, and each of the factor A and factor B, they had 2 levels which were denoted by A0 and A1, and in case of B it was denoted as a small b0 and a small b1, and equivalently these 2 levels were also denoted by 0 and 1 in case of the 2 factors A and B. And we also had explained, but I will try to have a quick review, that we had 4 treatment combination. I have here 2 factors A and B, A0, A1, and here B0 and B1, and based on that I have here 4 treatment combination A0, B0, A0, B1, A1 B0 and A1 B1. So, these 4 treatment combinations I have written over here. Now, in the theory of factorial experiment we have got different notations to express the same treatment combination. For example, this A0 B0, this can also be denoted as 0 and 0. How these zeros are coming? This 0 corresponds to this 0 and this 0 corresponds to this 0. And similarly, if I try to take A0 B1 here, then this 0 and this 0, they are the same, and this one in B1 and this one here in rectangle, they are the same. And similarly, if I try to consider here A1 B0, then in this expression the 1 of A and here this one, they are the same, and this 0 and this 0, they are also the same. And similarly, if I try to consider here the 4 treatment combination A1 B1, so this one is the same as here this one, and this one here is the same as here this one. So, this is another approach to express the treatment combination using the levels 0 and 1. And beside this thing, there is another alternative, that if you try to just consider A0 B0 as something like here A raised to the power of 0 and B raised to the power of 0, then this will become here 1. And similarly, if you try to consider here A0 B1, and if you try to consider as if this this subscript becomes the power, so this become A raised power of 0 and B raised power of here 1. So this becomes here 1 into B, which is equal to here B. And similarly, if you try to take here A1 B0, which is which I can write down A raised power of here 1 and B raised power of here 0. So this will become here A into 1, which is equal to here A. And if I try to write down here A1 B1, so this will be A raised power of 1 and B raised power of 1, this becomes here A into B. So in this case, what I would like to point out, that although I am not doing a mathematical operation, but this is another way to understand it, that how this different way of notation is derived. So in so the treatment combination where both the factors are at 0 0 level, this is denoted by here I. Try to see this circle. And similarly, this quantity here 0 1, which is here given here like this, this is denoted by here A. And similarly here A1 B0, this is denoted by here B, and A1 B1, this is denoted by here A into B. There is another nomenclature to this A0 B0, or the levels 0 and 1. Whenever we are using the symbol here 0, this is referred to as low level, and when we are trying to use the symbol here 1, then this is referred to as high level. And similarly, this identity matrix, this identity, this I here, this essentially denotes that both the factors are at lower level, that is 0 0, and this is also called as control treatment. That is the standard terminology what we are going to use in the case of factorial experiment. So these are different ways by which you can denote the different treatment combinations, and one can use any of the approach, they will give you the same output. Now let us try to come on another aspect, but before I do any further step, let me explain you here one thing, that you see when we wrote A B, what was the meaning of this? The meaning of this was that the factor A and B, they are at, both are at higher level, right? And when I am trying to write down this bracket here, so bracket is trying to give me the total yield, that if I take a plot and if I try to give here two factors A and B, where I am using the higher level of A and say here higher level of B, then whatever is the outcome here y, that is going to be denoted here as a and B. That is the standard notation, right? So, but now I am simply trying to use a wrong mathematical concept, and just for the sake of understanding, I will write AB as say here A into B. Well, I am saying again, this is not mathematically correct or statistically correct, but this is only a symbol, this is only a notation, and this type of symbolic representation will make the representation in the factorial experiment for various types of expression easy to understand. So you may now recall that in the earlier lecture we had found the main effect of irrigation and main effect of nitrogen, and out of them we have denoted them by factor A and B, and we had found the main effects of A and main effects of B. And you may recall from the earlier lecture that this expression was found to be like here this. So now what I am trying to do here, that I am simply trying to write down this AB here as say AB, and I am going to treat it as if this is the mathematical expression. So, you can see here I am trying to write here this here like this. So, I can write this expression here as a plus a b minus 1 minus b divided by 2, right. And just for the sake of convenience, if I try to write this thing in a mathematical format, I can write down this a will come out as common 1 plus here b minus 1 plus b divided by 2, and so I can write down here as a minus 1 into say here b plus 1 divided by 2. On this I am trying to represent here as like this. Now, from this expression what you have to observe, that I had two factors here a and b, and out of this you are trying to find out the main effect of a. So, once you are trying to find out the main effect of a, then in case if you try to look at this expression, right, then you try to see here that there are two types of symbol, plus 1 and minus 1. So, if I am trying to consider here the main effect of a, then the symbol corresponding to a comes here with minus 1, and the factor b, for that this appears here as a plus 1. So, as a rule of thumb, what I can say here, that in case if I want to write the main effect of a in a 2 square factorial experiment where there are two factors a and b, then the main effect of a can be written as say here a minus 1, because this a and this a, they are common, a is a, and whatever is here b, other factor which is not present here, that will appear as a plus 1 sign. And similarly, if you try to repeat the same exercise in finding out the main effect of b here, then you can recall that in the earlier lecture formally and statistically we had obtained this expression. Now, I try to do the same exercise here, and I can write down here the same thing here as say here b plus a into b minus 1 minus a divided by here 2, and this I am trying to represent here by here like this. So, now in this case you can see here that when I am trying to write down here the main effect of here b, then here a is not present. So, the factor which is not present, I will try to use the symbol here plus 1, and for the alphabet which is common, I will try to use here the symbol minus 1. So, you can see here this b is here and this b is here. So, now what I will do here for this effect which is present here, this I will add here minus 1, and the factor a which is absent in the main effect of b, I will try to use here plus 1. So, this is how I can write down here the main effect of a and b. Now, similarly, if you try to use the same philosophy here, now I am trying to find out the interaction effect of which is here a b. Now, in this expression a b, both a and b are present. So, I can use here minus 1 for this A and minus 1 for here B, and this expression has been derived using the proper statistical formulation. For example, in the last lecture you had obtained that the interaction effect between A and B can be obtained by this expression, and if you try to do here the same algebra, you will come to the same expression A minus 1 into B minus 1 divided by 2. And the final expression we had obtained in the earlier lecture, the general mean effect, which was simply the mean of all the observations. So, there were 4 observations. So, their sum is obtained in the numerator and it is divided by here the total number of observation, which is here 4. Right. So, the same technique can also be applied here, and we will arrive at this expression, which is A plus 1 and B plus 1. So, now you will see here that when we are trying to consider here the general mean effect, then in both the cases of A and B, only plus 1 will occur. Right. So, this is what now we have understood, that in case if I want to write about A, so I will try to write down here A 1 and here B 1 divided by here 2, and then since A is appearing here, so I will try to write down here A minus 1 and B is absent here, so I will try to write down here B plus 1. Similarly, if I want to write about here B, so I will write here A 1 B 1, and since A is absent here, so I will try to write down here plus 1 and B is present, so I will try to write down here minus 1 divided by 2, and similarly here A for the AB, I will write here A 1 B 1 divided by here 2, and both A and B are present, so I can write down here A minus 1 and B minus 1. And for here M, for the general mean effect, I will try to write down here A 1 and here B 1, and in both the cases I will try to write down here plus 1, but the divisor here is going to be 4. So, one thing what you have to notice in both these slides, which I will now try to highlight with the red color, that when we are trying to find out the main effect of A, then the divisor here is 2, you can see here. And when we are trying to find out the main effect of here B, then my divisor here is 2. And when I am trying to find out the interaction effect of A and B, then again my divisor is here 2. And when I am trying to find out the general mean effect, then my divisor here is 4. So, one question comes here, how these divisors are chosen, that sometimes they are 2 and sometimes they are 4. Yes, there is a strong there is a proper statistical theory behind this thing that we will try to discuss in the coming slide. But at this stage you have to simply take it here as a say here 2 and 4. Now, beside this thing, right, I will I have given here these things in more detail here, because for your understanding, so that you can now see I am trying to write down here the same thing, that you have to just notice the positive and negative signs as well as the divisor. There are 2 effects which are related to here A and B, right. And then, well, in case if you want to obtain here the main effect of A, then you have to write down here minus, otherwise you write down the plus sign with the remaining aspect. So, this is the same thing which I have given here in more detail for your more understanding, right. So, that is the same thing what I have just explained you. Right. Now whatever I have done here, I tried to compile it in a simple table. now you can see here these are the main effects of A and B, this is the interaction effect A B, and here the general mean effect. You can see here that there are only 4 values here, 1, A, B, and here A B. Yeah, this should be here something like this. Okay. Right. Okay. And now these 4 values have been combined in different ways to find out the main effect as well as the interaction effect. So, these 4 values can be combined in a simple table. So, this table is like this, that in the first column I am trying to write down here the factorial effect, which are here general mean effect, factor A, main effect of factor A, main effect of factor B, and interaction effect of the 2 factors A B. Now, I try to write down here the 4 treatment combination which are here, 1, A, B, and A B, and now try to look at the expression here M in green color. Now, you can see here that in this expression what is the coefficient of A B, which is here plus 1. And what is the coefficient of here A? This is plus 1. What is the coefficient of here? Plus 1. And what is the coefficient of here 1? This is here plus 1. So, all A B and 1, they have got the coefficient plus 1. This same thing is written here. This is here 1, its coefficient here is 1. This is here small a, whose coefficient here is plus 1. This is here B, whose coefficient here is plus 1, and this is here AB, whose coefficient here is plus 1. And this is the divisor here 4, which is corresponding to this thing. Right. Now, I try to take here main effect of A in this violet color, and you try to observe the movement of my pen with this violet color. So, you can see here in this case the coefficient of A B is plus 1 and coefficient of A is plus 1. The coefficient of B and 1, they are minus 1 and minus 1. So, these coefficient I am trying to write down here in this row. So, you can see here the coefficient related to 1 here is minus, which is minus 1. The coefficient related to here A, this is here plus, which is plus 1. The coefficient related to B here is minus 1, and the coefficient related to AB here is plus 1. And this is here the divisor. This divisor here is from here. Right. And the same thing I have done for this B and AB also. So, now what is the advantage of this table? By looking at this table, you can see here I can write any of the effect. For example, if looking at this part, which is here in black, right, I can write down here what is the main effect of here B. The divisor here is 1 by 2. So, I will try to write down here 1 by 2, and then I will try to write down here, this is here minus 1. So, minus 1, this is here minus A corresponding to this A, minus A, then this is here plus. So, this is here plus B, and this is here plus, this is here plus AB. Right. And you can verify here, this is the same thing which is written here in this case. And yes, now you can try to write down the same expression for AB also. So, I will not do it here, but I will leave it for you that you try to look at this expression and try to compare it with this expression in red. So, well, the slide has become a little bit clumsy, but by different colors and the movement of my pen, possibly you can understand it. Right. Now, the question comes here, when I am trying to deal here a 2 square factorial experiment, then I had told you that this I am going to consider under an RBD, that is randomized block design. So, how this model is going to be written, right. So, but if you try to see here, there are 4 treatment effects. What are those treatment effects? A, B, and here general mean effect here M. So, now if I say that there are n number of observations which are obtained for each treatment combination. What does this mean? That I have got here 4 plots in which I try to give here or let me try to write in this way. I have got here these here 4 plots, 4 treatment combinations are given, and for every treatment combination I have obtained here n number of observations. Right. So, now in this case this model will be written as say yijk, which is the kth observation which is obtained when the ith level of A and jth level of factor B is given. So, this is the meaning of here yijk, which can be written as here as a mu plus ai plus bj plus interaction effect AB and plus random error component epsilon ijk. So, this is the basically the model which is going to be considered for the analysis of variance, right. And definitely when we are trying to conduct the experiment factor by factor, then definitely more resources are needed if you want to compare all the different combinations of factors, and that we had discussed in the first lecture also, that this is a situation where factorial experiments comes to help us. So, now let me take an example and try to show you here how this factorial experiment helps us in using the smaller amount of experimental material. So, suppose I want to suppose I have here the 3 levels of nitrogen, that is the same thing that we had considered in the earlier lecture in the example. So, there are 3 levels N0, N1 and N2, and there were 2 levels of irrigation I0 and I1. Now, in this situation, if you want to have 10 degrees of freedom which are related to the error variance, that is SSE, then in this case you need to have 6 replications on nitrogen, 11 replications on the current, irrigation. So, it should be here irrigation, and so the total number of plots which are needed, this is here 40. But in case if you want to do the same experiment under the factorial setup, then there will be 2 factors and there will be all together 6 combination. What will be those 6 combination? Say N0 I0, N0 I1, N1 I0, N1 I1, N2 I0 and N2 I2 I1. So, these are the 6 combination. So, in this case, if you want to have the same outcome, that is the 10 degrees of freedom for the error variance, you need only here 18 plots, right. So, you can see here that in case if you want to use here simply the RBD in that traditional way, then you need here 40 plots, but if you want to do the same thing using the factorial experiment, then you need only here the 18 plots, right. So, there is a significant amount significant reduction in the number of plots. So, that will essentially save your cost, time, energy, labor, etc., everything. Right. Okay. So, up to now we have considered that there is only one observation per cell, and based on that we have obtained the main effect AIB and their interaction affect AB. But if suppose I want to repeat it, I want to replicate it, and suppose there are R replicated observations required for each of the treatment combination, then in that case the main effect and interaction effects along with the general mean effect, they are going to be computed as an average based on the R replications. So, in this case this divisor will become here 2R in case of A, B and here AB, and the divisor in the general mean effect, that will become here 4R. Now, you can very easily understand that why I am trying to take here R in the divisor, because now this is an average which is based on R values. That is the same thing that we had derived in the earlier lecture, but there because of the limitations in the presentation and in the slides, I could take only here there one observation, but if you try to increase it to R, then there are R observation, and for which you have to take the average, which is denoted here by 2R and 4R. So, that should not be a problem. Now, I try to convert it into a more mathematical and statistical framework. If you try to see here, let me try to first explain you here, and then I will come to a more formal way. Right. If you try to see here, what are these things? I can write down here 1 upon 2R. What is this here AB? This AB is the value of Y, that is the output which is obtained after giving the treatment combination AB. And similarly, what is this here A? This A is essentially here the value of the response or the yield which is obtained after giving the treatment combination here A. That means the lower level of B and upper level of A. And similarly, when I try to give here the use here the treatment combination here B, then the response is denoted by here YB, and this for this identity I am writing here Y here 1. So, in some sense I can write down here is something here like this, that this is here means if I try to write down here in a more simple way 1, say here A, B and here AB, then I can rearrange this term here as say this Y1, this has -1 coefficient, so I can write down here -1, then here A, this A here, this A here as a +1, so I can write down here +1, then this here B, this B here as a -1, so I can write down here -1, and then this here AB, because is here +1, so I can write down here +1. So, I can write down here 1 upon 2R, and yeah, this I can write down here L vector, which is corresponding to the main effect A. So, I can write down here LA prime, and this is my here some vector here Y, which is here connoting something like Y1, YA, YB and here YAB. Yeah, to be more precise, I can write down this vector as a like this. Right. So, now you can see here that this is a linear parametric sorry, this is a linear combination of the Y1, YA, YB and YAB. So, I have expressed this thing here as say here like this, and similarly I can express the main effect of B, interaction of effect of AB in this particular format. So, you can see here this Y here remains the same in all the expression, which is here y star, y star, y star. Even this 2r will also remain the same. What is changing here? This is only here the placement of +1 and -1, you can see here. And you can observe one very important thing here, that all these linear combinations, they are linear contrast. You can see here in this case -1 + 1 -1 + 1 is equal to 0. In this case also -1 -1 + 1 + 1 is equal to 0. In this case 1 -1 -1 1 is equal to 0. So, they are in the form of a linear contrast. And you may recall that in the initial lectures we had discussed that a linear parametric function is estimable only when it is in the form of linear contrast. And that is the reason that this theory has been evolved in such a way such that this A, B and AB, they can be represented as a linear orthogonal contrast in the total response values, which are 4 values here y1, ya, yb and yab, right. And obviously now you understand that this factor 1 upon 2r how it is coming, because that is coming because we are trying to measure different types of component from the same set of observation, and for that now I can say that the main effect, interaction effect and everything that has been obtained by those only 4 values by considering different type of linear contrast, right. So, now the next question is this: when we are targeting towards the analysis of variance, then we know that how to compute the sum of squares of a linear parametric function, right. So, if there is estimated L transpose y of the linear parametric function, then the sum of squares of this linear functions is computed by this expression, which is L transpose y whole square upon L transpose L, right. And if but this is based on the assumption that there is only one observation for each treatment combination, and if there are R replicates, then this sum of squares will be changed to this expression, where I have added only here R in the denominator. So, this is how we can consider the we can find the sum of squares. Now, using this theory, I can compute the different types of sum of squares for this here A, for this here B and for AB. So, I have computed here sum of squares due to A by this expression, and means you can see here now I am using here L prime A, which is the vector of +1 and -1, in which the +1 and -1 they have been arranged in a particular way, right. And similarly for the sum of squares due to here B, I am trying to write down here the similar thing, L transpose B y star whole square divided by R into L transpose B into LB. And if you try to see here in both these cases, LA prime LA will come out to be here 4 if there is there are one observation for each of the thing, and if that is repeated, say this R times, so I will add here 1 upon 4R, which is being done here. And the same thing will happen in case of here SSB and SSAB. And now we also know, because we are assuming that that y's are following a normal distribution. That is one of the basic assumption in the linear model under this analysis of variance. So, I can say that these sum of square SSA, SSB and SSAB, they are following a chi-square distribution with 1 degrees of freedom, right. So, this SSA, SSB and SSAB, they will have 1 degrees of freedom, right. And after this, the total sum of squares, that is computed by the usual expression, which is here sum of squares of all the observations like this minus here correction factor g square by n, and n here is by here n, and where n here is 4r, and what is here g? G is the grand total which is obtained here as sum of all the observation. And one can find out here very easily that this TSS we will have here 2 square times r minus 1 degrees of freedom, which is equal to here 4r minus 1, and that if you try to see, this is equivalent to means something like saying this has got n minus 1 degrees of freedom, right. And after this you can compute the sum of squares due to error by the usual expression TSS minus SSA minus SSB minus SSAB, and this will also follow a chi-square distribution, and whose degrees of freedom can be obtained by subtracting. The TSS has 4r minus 1 degrees of freedom, SSA has 1 degree of freedom, SSB has 1 degree of freedom, SSAB has 1 degree of freedom. So, this will come out to be that SSE has got 4 into r minus 1 degrees of freedom, right. And after this you can derive the F statistics for testing the significance of factor A, factor B and factor AB. So, that will be simply be the sum of squares due to A divided by the degrees of freedom, which is here 1, and divided by the sum of squares due to error divided by its corresponding degrees of freedom. So, that will follow a F distribution with 1 and 4r minus 1 degrees of freedom under H naught, and similarly the F statistics for factor B and for the interaction AB, that can also be obtained exactly on the same way. For example, in the case of B, this is SSB divided by degrees of freedom 1 divided by MSE, which is the same as SSE divided by degrees of freedom, and in case of AB, that is sum of square due to AB divided by the degrees of freedom divided by sum of squares due to error divided by the degrees of freedom. So, this is how we can find out the required statistics to test our H naught related to A, related to B and related to AB, and all these results they can be combined here in this ANOVA table. So, this is the standard ANOVA table. In the first column we have a source, which are A, B, AB and obviously error and total. Then we obtain the sum of squares, which are here SSA, SSB, SSAB and TSS, and then from there we try to obtain SSE. SSA has got degrees of freedom 1, SSB has got degrees of freedom 1, SSAB has got degrees of freedom 1, SSE has got degrees of freedom 4r minus 1, and finally TSS has got degrees of freedom 4r minus 1. And then based on that we can obtain the mean square due to A, that is SS sum of square divided by degrees of freedom, mean square due to B, this sum of square due to B divided by degrees of freedom, and mean square due to AB, this is SSAB divided by degrees of freedom, and similarly we can find out here MSE, which is SSE divided by degrees of freedom, and then based on that we can obtain here the 3 F statistics related to the factors A, B and interaction effect AB. So, right, and in case if you want to take a decision, we have the same rule that we have discussed many times in the past in the case of analysis of variance, that we will reject the concerned null hypothesis when the F statistic that you have obtained on the basis of given set of data, which is FA, FB or FAB, they are greater than their tabulated value, which are obtained from the F table. So, right. So, this is all about the 2 square factorial experiment. So, if you try to see in this lecture what I have done, I just took the same example which I have considered in the last lecture. There I had taken 2 levels, irrigation and nitrogen, and now I have formalized it in the standard symbols like as say capital A, capital B for the factors and the small letters for the levels. Then from those 4 values of treatment combinations, I have shown you that how you are going to compute the main effect of A, main effect of B and the interaction effect A B. And then obviously computing the general mean effect is straightforward. So now what you have to remember one thing, that all this main effect and interaction effect, they are being estimated as a linear function of y, and this linear function of y is in the form of a contrast. And why this is in the form of the contrast? Because we know that a linear parametric function is estimable only when it is in the form of a contrast. That is the first thing. Second thing, that how to conduct the analysis of variance, for which I need the ANOVA table. The ANOVA table has a couple of components, like what are the different sources, what are their degrees of freedom, what is the how to find out the sum of squares, and then how to find out the mean squares, and then finally how to find out the F statistics. So I have shown you that how to compute the main effect of A, B and interaction effect A, B. Then I have discussed that in the case of 2 square factorial experiment, which is now converted into a linear function in the form of a contrast, how you can compute the sum of squares. Now, based on those sum of squares, I can compute the mean squares also, because each sum of square is following a chi-square distribution with 1 degrees of freedom, and from there I have constructed the F statistics. Right. So my objective was very simple in this lecture, that using a very simple setup of 2 square factorial experiment, I wanted to show you that how these things are developed further up to the level of finding out the analysis of variance table. Now, the same concept can be extended to 2q factorial experiment, or in general to any 2 raised to the power of n factorial experiment. Think about it. And in the next lecture, I will try to take an example of 2q factorial experiment, and whatever I have done here, I will try to simply extend it mechanically. One of the important point which you have to keep in mind, once I do it mechanically, the things becomes very simple, but the main objective of my lecture was to show you, was to demonstrate that how those things which are obtained mechanically are really originating. So you try to revise this lecture, try to understand it, and in the next lecture I will come up with the 2q factorial experiment. Till then, goodbye.